Hi, I'm going to present you the paper To Boldly Go Where No Fuzzer Has Gone Before, Finding Bugs in Linux Wireless Stacks Through Word.io Devices. My name is Huster and I'm currently a PhD student at the University of Göttingen, and I wrote the paper together last year at my time at the Secure Mobile Networking Lab at TU Darmstadt, Germany, together with Matthias Hollig and Jiska Klaassen. So, as you might see from the title, we've built a fuzzer for Linux wireless stacks, and it had quite some pretty good results. We found several remotely exploitable Linux kernel Wi-Fi vulnerabilities and got quite some media coverage. But before I tell you more on our fuzzer, I want to get everybody on the same page on what fuzzing is. Fuzzing works like that. The fuzzer has a set of inputs. It selects one of those inputs and does some mutations. Those mutations can be bit flips or combining several mutations together, but also the removal of several bytes. This new mutated input is then fed into some target. For us, these are the wireless stacks. And the fuzzer watches the target executing on the frame, processing the frame, and sees whether the input crashes or doesn't crash. If it does crash, we have a solution. We kind of find a bug and we want to investigate that, so we save it for later. But most of the time it doesn't find the crash, so it has to decide whether the input improved somehow the state. If it didn't improve, the new input is just discarded, but if it was improved, the mutated frame is saved for later. This process goes all and over and over again, 1,000 times a second, so that in the end our database might be filled with several frames crashing the target that we can then analyze. So there have already been fuzzers for the Linux kernel before. Why did we build our own? Well, we had several design goals in mind. The first design goal was depth. We had the feeling that some parts of the kernel, especially for wireless subsystems, are not covered that well with existing solutions. So our biggest goal was to cover previously uncovered kernel parts. The second goal was authenticity. We thought that a fuzzer who starts with authentic seeds might get better results. So we wanted to build a fuzzer that uses real-world inputs as genuine seeds when it starts fuzzing. The third one, extensibility. We tried to adapt several fuzzers to our targets, and it was kind of a lot of effort. So our third design goal is easy adaptation to different interfaces, so that even new targets can be added easily. For this extensibility, we are using Word.io. I give you a short introduction on what Word.io is. This is from the Word.io standard. Word.io devices are found in virtual environments, yet by design they look like physical devices to the guest within the virtual machine, and this document treats them as such. This similarity allows the guest to use standard drivers and discovery mechanisms. So what we did was we've built a Word.io device for fuzzing. Those Word.io devices are built in the hypervisor. We are using QEMU, and usually they contain the state so that they can emulate such a device. So for example, if you would build a Bluetooth Word.io device, you would patch QEMU and have all the Bluetooth logic in that device. And when then QEMU starts a virtual machine, this device tells the virtual machine that it is a Bluetooth Word.io device, communicates over PCI, both negotiate some features and provide configuration, and in the end communications happens through word queues. But we don't need any certain logic of a special device for fuzzing. We just want to get inputs in and out. So what we did was that we've built a universal Word.io device. The universal Word.io device starts with reading some device configuration. In our case, it's just a JSON file. Most importantly, there's the Word.io ID, which specifies which device is used. And then there can be other information, such as certain configuration information, certain features that you can see in the standard that are available, and also most important, which indices, which queues are used for transmitting and receiving frames. And our universal Word.io device that we've built into QEMU now reads such a configuration and initializes then as a specific Word.io device and does the several steps that I've shown you before. So that means that the virtual machine thinks there is a normal, for example, network device, but it's just our fuzzer. And the thing is, it doesn't communicate in the end and does all the stateful stuff, but it just sets up those word queues and tunnels them to a Unix socket so that those word queues are available to our Linux kernel fuzzer. We first used those this universal word I/O device to collect inputs that were authentic. Therefore, we built a small proxy that connects on the one hand to the virtual machine, but on the other hand to the real hardware. So for example, the Bluetooth controller. And then we used the Bluetooth controller from within the virtual machine, paired several devices, real world devices, and the proxy collected all the inputs that were generated during that and saved that for later so that we could use them to start fuzzing. So now let's take a look how our fuzzer actually works. Our fuzzer uses a word I/O driver of the configured subsystem to fuzz the subsystem behind. This Linux kernel runs in QEMU, which we patched with our universal word I/O device, and our fuzzer uses the universal word I/O device to send inputs to the virtual machine. Furthermore, we are using kcuff. Kcuff is a coverage mechanism for the Linux kernel, and it usually works from user space, so you have to do some system calls to configure which coverage should be collected and when. But we don't want to make system calls from user space because we are not in user space, we are just outside. So our fuzzer also contains a patch for kcuff so that those coverage information is written to some shared memory between wordfuzz and the Linux kernel. Furthermore, we need to detect crashes. We simply do that by parsing the kernel log. The kernel log contains a lot of information, and if there's some problem or if some sanitizer finds a problem, it is written in the kernel log. So before I said the coverage must be started from user space, and we did some patches. The patches that we did to start and stop coverage collections are simply two function calls. So you need to annotate the code that you want to fuzz, for example, the network subsystem or the Wi-Fi subsystem, with those small functions around the entry point so that kcuff knows when to start and when to stop writing to the shared memory for coverage collection. We are able to collect two types of coverage. First, normal AFL style map coverage, and the second, comparisons tracking, which is based on the Red Queen paper of Asherman et al. With those comparisons, we can overcome magic blocks and several more issues, which are way harder to overcome with the normal AFL style map coverage. Furthermore, we are using libafl for some parts of our fuzzer. Libafl is the fuzzer library, so they provide several building blocks to build your own fuzzer, for example, mutators or input schedulers. So that was really helpful, and you don't always have to invent the wheel from the beginning. There's also a paper worth reading on that. So now I'm coming to the results that we had when running our fuzzer. First, I already teased that in the beginning. We found several Wi-Fi vulnerabilities. We found a heap overflow, used after free bugs, null pointer references, and infinite loops. And in total, we got 5 CVEs for those Wi-Fi vulnerabilities assigned. With those vulnerabilities, you can at least do a denial of service attack, but possibly also remote code execution. And the thing is that they are quite impactful because they don't require user interaction. The vulnerabilities that we found are in Wi-Fi beacon frames. And beacon frames are the frames that your phone or your computer just receives to see which networks are in the area. So you don't have to trick the user to connect to a malicious AP or something like that. You can just exploit that with those beacon frames. And I already said it on your phone, they also affect Android, at least partially. So I guess that's why we got some media coverage. So let's come to our total results, not only the bigger Wi-Fi issues. In total, we found 31 new vulnerabilities and got 6 CVEs assigned. We found 16 in the Bluetooth stack and 15 in the Wi-Fi stack. And as you can see, we found all kinds of memory bugs or memory vulnerabilities like memory leaks, null pointer dereferences, slap out of bounds, use after free, also integer underflows, infinite loops, and yeah, so quite a lot. And those vulnerabilities that were not just introduced in the kernel, but some of them stick really for a long while around. Here, for example, is a table of all our findings in a more detailed way. And you can see that some Linux versions are kind of some years old at least. Like Linux 5.1 was the earliest version, which was affected by some of our Wi-Fi vulnerabilities. And Linux 2.6.27 was already vulnerable for some of the Bluetooth stuff that we found. So our first design goal, depth, I would say you can see that we did cover some parts of the kernel that were uncovered before because we found several severe vulnerabilities. But we also did a more formal evaluation against syscaller in Wi-Fi and Bluetooth. Here you can see our fuzzer in blue and in orange and syscaller in green. You can see that our fuzzer has a better basic block coverage compared to syscaller on our test over 24 hours. Furthermore, there is a difference between the blue and the orange configuration. The orange configuration just started with some random inputs, and the blue evaluation starts with some collected inputs from our proxy. So as you can see, the collection of real-world inputs has some impact because it accelerates the fuzzing process. It gets kind of a head start of several hours, but also you can see that the fuzzer with just random inputs reaches a similar coverage after a certain amount of hours. So collecting authentic seeds just gives you a head start of several hours, as far as our experiment shows. We also took a look at the functions that were covered by syscaller and by wordfuzz, and we saw that in total wordfuzz covered 162 functions, syscaller did only cover 96 functions in the block. Only 7 of those 96 functions were not covered by our fuzzer wordfuzz, so you can see we cover a whole lot. Now I want to give you a short insight in our design goal extensibility. To add a new device, you simply have to provide a short JSON file, which is the Word.io device configuration, which contains the stuff that you can see on the slide. Furthermore, you need the patch with the kcuff annotations that I talked about before. Those kcuff annotations are rather small. As you can see here, the kcuff annotations that are required to efficiently fuzz the Bluetooth subsystem are light, only change 2 files, have 12 insertions and 2 deletions. So thank you for listening. I hope it was a bit interesting, and if you want to find out more, read our paper To Boldly Go Where No Fuzzer Has Gone Before, Finding Bugs in Linux Wireless Stacks Through Word.io Devices. Our code is also available on GitHub under GPL license, so you feel free to run it, to try it out. You can find the link to GitHub on this slide. Thank you for listening.